Next, we want to introduce the indicator function, or it's also called the characteristic function, and it's some very important, sorry about this, some very important notation and IDs for one very simple reason is that when we're going to do some integration, by default, we will always integrate on the whole of R, and if we want to restrict the integration, we will need to most of the time to use this kind of function to define the set where we want to do the integration. So to have an indicator function, we need the set. It's going to be the indicator function of the set. It's defined like with this symbol, this one written like this. That's like kind of blackboard bold one with a double bar, 1a. So in subscript, you write the name of the set that you want to indicate, and it is a function. So it's depending on x. By default for us to begin with, it's always on R, on the whole of R, and it's just a function that takes one if x is in A and 0 otherwise. So if A is just a simple interval, that's the function. Let's say that it's the interval AB. Your indicator function is the function that has 0 value outside of the interval and value of 1 inside of your interval. Okay, so this is a very convenient one. It's just this kind of door gate function that allows you to say, well, it's 0 except for my set. But of course, your set could be much more complicated than just an interval. Some other notations that you may encounter is key. That letter, that Greek letter, is the key, for characteristic function, key of A. All right, and from this indicator function, we can define the value of its integral, of its Lebesgue integral. So as it's with respect to some specific measure, right? Measure mu. So for us, again, we will use the just the most simple measure. It's called actually the Borel measure that we have. It's just the usual measure. Just remember that for interval, it's the size of the interval and the measure of isolated points is just going to be equal to 0. But the construction of the Lebesgue integral goes like this. We can define the integral of any indicator function. It's going to be exactly equal to the measure of your set of the that is indicated, right? So that's simple. And from here, so let's sum up. We define indicator function like this. We define the integral of indicator function. So let's start to see what it means. What it would be the integral of the indicator function when your set is AB. So it's going to be equal to the measure of A, which is the measure of interval AB, and whether it is open or closed, it's the same measure. So let's say I'm opening it on one side, closing it on the other side. If you remember, we've already used that kind of idea that just one single point doesn't have any width. So the measure of this interval, whether it is closed or open on either side, that's going to be B minus A, right? Measure of points. So let's say you've got point A, point B. So measure of that whole interval, that's B minus A. Measure of isolated points. Let's say I just want point A, I just want point B. Let's say I've got other points. As long as they are isolated, indicated by this notation, the measure here is going to be equal to 0. Right? And that's one of the very common examples. That was one of the examples that actually Lebesgue showed to motivate the introduction of his new kind of integration. Q. What about Q? Q, the set of fractions, of numbers that can be written as fractions of rational numbers. What about this? This is actually, there's a whole theory that unfortunately you probably didn't have time to see in first year and not in second year. Q is a countable infinite set, but it's still made out of isolated points. It is dense in R, meaning that you can approximate as close as you want any real number by a fraction, by a rational number. However, the measure of Q being isolated points, the measure of Q is equal to 0, although it is absolutely dense in R. Okay, that's one of the beauty of this. So we could even take the integral of the indicator set of Q, and in that theory, that would be equal to 0. Okay, because we have stated it like this, right? This is how it is built, so that we have a good measuring function, right? So so we know how to take integrals of any kind of sets that we're going to consider, as long as we've got a measure. So from this, we're going to define the integrals of simple functions, just like when you were doing with Riemann functions. With Riemann integral, you were defining the integral of step functions as being the sum of those rectangles. Here we are going to have something quite similar to step functions, but it's simple functions. In French, the French word for that is fonction étagée. Step functions were fonction escalier, but here we've got simple functions, which are actually, sorry, there is something missing here. It's linear combination of indicator functions. Okay, so something like this. So that's a coefficient times an indicator function. If I take sum of this is exactly a linear combination of indicator function. And from that, using the linearity of the integral, I just get that it's the sum of the coefficients times the measure of the indicated set, right? So I will have an example here. So simple functions, sorry, again, this one has disappeared. So that's a simple function. And so we define the integral of that. What's the difference between a simple and a step function is that here you see we've got two intervals where the function takes the same value. And this is going to be defining one single set. Here it's called A3. So when I'm going to calculate this integral, I will take, so let me take a nice color, the measure of that A1 times the value small a1. Then I will take the measure of the a2 interval times the value here. And then I will take the measure of the a3 set, which is made out of those two intervals times one, well, that's single value. Okay, so it looks very similar, but it allows for more possibilities. What I want to yeah, and we will see another animation that is quite nice to show the difference between Lebesgue and Riemann integral. But the idea is that now that we know how to make the integral of simple functions, we can we could show, we're not going to do it because it's quite technical and well, it's a bit beyond what we want to do in our class. We can show that any measurable function can be approximated by a sequence of simple functions, and so we can define the integral as the limit of the sequence of the integral of the approximating sequence. So either this integral is converging and then this the integral of this function is converging, or if it's not converging, then it's not converging. It's not going to be called Lebesgue integral. Okay, so here we've got some nice drawing that is trying to show you. So these two graphs, they come from Wikipedia. They are the chart of COVID cases at some point in some place. All right, so you've got a nice function. If you wanted to do the Lebesgue integral, you would proceed this way, meaning you would discretize your the interval, and then do the sum of the areas of the corresponding rectangles. If you want to do the Lebesgue integral, this is how you would do. You would, instead of discretizing the interval, you would discretize the values that your function is taking, and in corresponding to these values, you would create, so that's for the first value, you get this first set composed of those two pieces. And for instance, let's take something that is maybe a bit more visible. For this value, this highest value that we take, we are going to keep one set that is composed of those two subsets here. Okay, so the whole idea of Lebesgue was, instead of doing discretization on the domain, it does discretization on the values that the function takes. So that in one sense, if this function takes some maybe infinite values, okay, it won't matter as long as the corresponding set is negligible. Okay, has zero measure. Let's have a look at this GeoGebra animation, which was quite a nice one. So that's the one. So let's replace. So on the left, you've got, I hope it's, yeah, on the left, you've got the Lebesgue. Sorry, you've got Riemann. Sorry, I can't write here. You've got Riemann on the left, you've got Lebesgue on the right. And so you see on the left, we've got discretization. So here we enhance the number of discretization. We've got discretization of the interval, and on the right, we've got discretization of the values of the function that the function is taking. Okay, and so this is what we would the different ideas. Of course, it gives you the same result, but this is the different idea behind those integrals. Okay, so let's get back to this presentation. Okay, just to begin to end with that. So now let's assume that you know that this integral is nicely constructed, and so we can make the integral of any kind of measurable function, so any kind of functions for us, as long as they are positive. We've shown that only for positive functions, and that's a common idea, that any function can be described as the sum of its positive side plus its negative side, but its negative values can be written as minus some f minus function that would be positive, so that in the end, using linearity of the integral, we get this definition. And what is important to note is that actually, in order for these two integrals to converge, we need that the integral of the absolute value of f is actually converging. Okay, because the absolute value of f is going to be f plus f minus. All right, so that's it here. Okay, so when we said that something is Lebesgue integrable, it's not only that the integral of f is converging, it's really that the integral of the absolute value of f is converging. Okay. So that these are Lebesgue integrable functions, all right? And so as you see, we no longer put any kind of bounds by default. What does it mean? It means that by default, it's always defined on R. And if we want to restrict the domain of integration, we are multiplying by an indicator function. That's one of the use of that, all right? And to finish with that, the properties of the Lebesgue integral are exactly the same as before. Of course, they do coincide, Lebesgue and Riemann integral. They do coincide when it's converging, when it's absolutely converging. So you've got linearity, as always. The integral of the sum is the sum of the integral. You've got positivity. Integral of a positive function is positive. And in particular, it means that if you've got two functions that are ordered, even ordered almost everywhere, that's going to work, then their integral are ordered. And you also have, of course, because that's a consequence of the previous one, that the absolute value of the integral is, if your integral is absolutely converging, like this one, integral of the absolute value is finite, then the other one is finite. Okay, so we will begin our important theorems next section.